Alright, let's take a look at an example involving a trigonometric function. Again, for this problem we are going to find the intervals where this function is concave up and concave down, and any inflection points, but we're going to restrict it to this closed interval. Of course, the domain for this function is all real numbers, but because of the periodic nature of the cosine function, we would have infinitely many intervals, for instance, where we're concave up, infinitely many where we're concave down, and infinitely many inflection points. So let's just look on the interval from 0 to 2 pi. So if you remember, what do we want to start with? Derivative, right? What's the derivative of this function? Well, theta is the independent variable here, so the derivative with respect to theta is 1, and the derivative of cosine theta is minus sine theta. And the second derivative, derivative of 1 to 0, derivative of sine of theta is cosine theta, so this is negative cosine of theta, right? Because it's 0 minus cosine of theta is the derivative. Okay, and so it's pretty easy here. The second derivative, therefore, is equal to 0 whenever cosine theta is equal to 0. When is cosine theta equal to 0 on this interval? Pi over 2 and 3 pi over 2. So what do we need to do now? Once we have our second derivative, we need to do a sign check of this second derivative. And it's on the closed interval, so I'll emphasize that with my real number line here from 0 to 2 pi. And the places of interest we have are pi over 2. And here would be pi, and then 3 pi over 2. So a second derivative we said is 0 in those locations. And then, as far as the sign check, it's if you notice, our second derivative is just negative 1 times cosine theta, so the sign is just the opposite of whatever cosine theta is. Remember, cosine theta of 0 is 1. It's 0 at pi over 2, goes down to negative 1 at pi, back up to 3 pi over 2 is 0, and then at 2 pi it's positive 1 again. So that's right, the graph. So that the negative cosine theta would just be reflection in the x-axis. So notice the sign is going to be negative, positive, negative. And again, you can just check representative numbers in each of these intervals and find the sign of the second derivative. Alright, so that's enough to tell us the answers, right? Where is P concave up for what values of theta? Where the second derivative is what? Positive, right? Where the second derivative is positive means the derivative is increasing, means that P is concave up. And then P is concave down wherever the second derivative is negative. Oops. 2 pi. That little mess up. And then, do we have any inflection points? Yeah, when theta is what? Remember, these are theta values, right? These are theta values here. Independent variables, theta. So, for what values of theta does that occur at? Where we have a sign change in the second derivative, where the second derivative is 0. So right there, from negative positive, positive negative, and pi over 2, and 3 pi over 2. Now, we do get in the habit of just saying, oh, every time the second derivative is 0, then maybe we have an inflection point. But that's only true, again, where we have changes in the sign of the second derivative. Okay. Let's illustrate that with this example. Suppose I say we have a function and I ask you where's the location of the points of inflection, assuming that f is continuous. Assuming f is continuous and f double prime is given as this. So I've given you already the second derivative, and remember we need to know first of all when is the second derivative equal to 0. Well, when is it equal to 0? This is completely factored, so for what values of x are we equal to 0? 0, -4, and 3. And let's do a sign check of f double prime. And we could do a sign check pretty quickly here. So at -4, we're 0. At 0, we're 0. And at 3, we're 0. And so I'm going to do a sign check of this. If I plug in a number less than -4, like -5, let's see what we have up here. Well, notice whatever squared and whatever to the 6th power, those are always going to be positive, right? Anything raised to the even power is positive. So that's positive, that's positive. It's just basically the sign of this thing. And x plus 4, when x is less than -4, like x is -5, will be -5. Plus 4 is -1, -1 cubed is negative. Okay, and in fact, it's pretty quick what's happening over here, but let me just say something too. Once you have a sign here, and you have a factor this way, do you remember what happens to this, to the graph of the second derivative at x equals 0? Notice this is a 0 of multiplicity 2. There's 2 factors associated with that 0. Right? For -4, it's a 0 of multiplicity 3. And 3 is a 0 of multiplicity 6. So you remember, for even multiplicity functions, the graph will touch the x-axis but turn around, will not cross. It only crosses the x-axis when the multiplicity is odd. And so what's going to happen at -4, the graph of the function is going to look something like this. At the graph of the second derivative, that is going to be at -4 is 0, but it bounces back around, and it's still negative here. And then at 0, even multiplicity means same thing. It's going to touch and turn around again, so back to being negative. Whoops, I said that wrong. At the 0 of -4 was odd multiplicity. Sorry, I don't know what I was thinking. It's odd multiplicity, so it's actually going to change through. I'm sorry. So all that. So it's going to cross through, right? Odd multiplicity. So this will become positive. And it's going to come around and just touch here, still be positive, and it's going to touch and turn around at 3 because 3 is even multiplicity, positive again. Okay. Didn't mean to confuse anybody there, but there's the graph of the second derivative. But there's the sign check. And you can see that because, again, for any value of x, this term and this term are positive. So the sign is basically the sign of x plus 4 cubed. Right? And x plus 4 cubed is negative if x is less than -4, positive if x is greater than -4. Okay. So how many inflection points does f have? Is it 3? Are each of these inflection points because the second derivative is 0? No. We only have inflection points when what? When there's a change in sign in the second derivative. So it only has an inflection point where? At x equal -4. That's the only place we have a change in sign, right? No change in sign, no change in sign. So that's what I'm saying. You've got to be careful. A lot of times I'll ask a question about how many inflection points does a function have, and I give you this second derivative, and this information is usually given. just because you're saying that's when the second derivative is 0. Well, it has to be a change in sign in the second derivative. It has to change from concave down to concave up, or vice versa. Okay. What I want to finish in this video with then is an example, a use of the second derivative for finding local extrema. So this is known as the second derivative test. And here's how it works. If the derivative at a point C is 0, and the second derivative exists on an open interval containing that value of C, then if that value of the second derivative at C, so I'm just evaluating the second derivative at C, if that's less than 0, then f of C is a relative maximum. If the second derivative at C is greater than 0, then f of C is a relative minimum. And then f double prime of C is equal to 0, then this test is inconclusive. In other words, it doesn't tell us any information. We would have to use the first derivative test that we talked about before. Now some of you might say, wait a minute, if the second derivative of C is less than 0, then there's a relative maximum. Less than 0, maximum, doesn't sound right. Remember, it's the second derivative less than 0. If this is the case, right, if the second derivative is less than 0, and this second derivative exists on an open interval containing C, then what do we mean? On that interval, the second derivative being negative means we're what? Concave down, right? So we're concave down, which means, you know, it could be increasing concave down, decreasing concave down, something perhaps like this. The question, though, at C, what's happening? The first derivative is 0. Where is the first derivative of 0 here if we're concave down? Right here. Where is that? That's what? A local what? Max or min? Local max. Right? This case, right, second derivative being greater than 0 means we're concave up. Right? Where is the first derivative of 0? Down here at the bottom at the local min. So you understand why this is true. The second derivative at C is less than 0, relative max. Second derivative greater than 0, have a relative min. Okay? If the second derivative equals 0, then we can't determine. It could be a max, it could be a min, it could be neither. It could be neither. Okay? And I can illustrate the inconclusiveness problem because these three functions at 0, what's happening? Well, if I take the first derivative of each one, what do we realize? 0 is a critical number, right? In fact, the f prime of 0 is 0, right, for each of these. But if I take the second derivative, well, in each case, the second derivative is equal to 0, right? At C equals 0, right? So f prime of C is 0, f double prime of C is equal to 0 for every single one of these functions. But clearly, if I look at the graph of x cubed, it looks like this, right? There's 0. Is that a max or is that a min? It's neither. It's neither. What about this situation? X to the fourth graph will look like this. What's going on down here where the first derivative is going to be 0? That's a local min. And what's negative x to the fourth? It looks like that. What's that point there? A max. So you see, if the second derivative at C is 0, it's inconclusive. I don't know. It could be a max, could be a min, could be neither. I don't know. doesn't work. All right, let's take a look at using the second derivative test then. And one thing nice about the second derivative test, we don't have to do a sign check. We just evaluate. We do have to find out where the first derivative is 0, so of course we need the first derivative. 3 times 4 is 12. Derivative of 2 is 0. So there it is. When is this 0? Let's factor. Greatest common factor I can pull out of this is a 4x squared, which leaves me an x minus 3. And so when is this function equal to 0? When x is 0 or 3. Okay. What do we need for second derivative test? We need the second derivative. What's the second derivative? Well, that's going to be 12x squared. 2 times 12, negative 24x. Don't need to factor this. I don't need to know when this is equal to 0. What the second derivative test says, check the values of x where the derivative is equal to 0. That's 0 and 3. Okay. So at x equal 0, h double prime of 0 equals what? 0, 0, 0, right? And so what do we know? The second derivative test is inconclusive. I would have to use the first derivative test to determine what's going on at x equals 0. Okay, whether we have a max or a min, or neither. At x equal 3, though, what do we get? 12 times 3 squared, 12 times 9, minus 24 times 3. 9 times 12 is 108. 24 times 3 is 72. 108 minus 72 is greater than 0. And what does that mean? Think about when we're greater than 0, if the second derivative is greater than 0, we're concave up. So what's happening at x equal 3 where the derivative is 0? We have a local min. So that's how we can apply the second derivative test. I do have an example of the graph, or have the graph of this function down below, and you can see as we've tested that at 3 we indeed have a local minimum. At 0 it actually turns out we have neither a local max nor a local min. But we would have to use the first derivative test to determine that algebraically. Okay, so next lecture we are going to be talking about limits again, everyone's favorite topic. We're going to come back to the topic of limits, basically look at how to evaluate some limits with a new rule, which you'll probably wish that we had when we first started talking about limits way at the beginning of the course. We're going to look at this, and this will basically complete what we need, the tools we need to analyze the graph of any function, and we will look at the graphs of any functions then in the following lecture after this little break into the world of limits again. So we'll do that in the next lesson.